Hey folks, in this video we're talking about thermal equilibrium. So we got a few objectives here. I want you to be able to define thermal equilibrium. Wow. I want you to be able to perform calculations relating to thermal equilibrium. Man, my words suck. And that's about it. So let's talk about thermal equilibrium and conservation of energy. Thermal equilibrium. If we have two substances that are mixed at different temperatures, two substances that are different temperatures, they're going to come to the same temperature when they're mixed. It might not happen immediately, but it will happen over time. So some examples of this are if you take some warm water and some ice and you mix those puppies together, eventually that warm water is going to cool down to the temperature of around that ice. Unless all the ice melts. But either way, they'll all come to the same temperature. Or if you stand outside for far too long in the winter, you're going to come to thermal equilibrium with your surroundings. So whatever temperature it is outside, you will be that temperature, and that might make you dead. Unless there's some weird climate change afoot. So conservation of energy, or winter view is somewhere tropical. Conservation of energy states that energy can neither be created nor destroyed. And so thermal equilibrium plays a part in this. Energy only moves between different substances or different forms. But like for you standing outside in the winter, your energy is going away to the surroundings. And there's a lot of surroundings in the winter time, all the time, when you're outside. So when two objects at different temperatures come into thermal equilibrium, the energy received by the cold substance is going to be equal to the energy that's lost by that hot substance. So another example, let's think about the ice and the water. When we put that warm water together with the ice, that warm water is going to lose heat to that ice. Some of the ice will probably melt, but there's going to be an exchange of heat, but it's not going to go anywhere else but between those two things, assuming they're well insulated. So the thing that is heated, the heat that it releases is, or rather, the heat that it absorbs is going to be equal to and opposite the heat that is lost by the thing that is cooled. The water is going to be gaining the same amount of heat that this ice is losing here. And so our final temperature should be the same for both of our substances. So this lets us do some cool things if we take our friend Q equals mc delta T, and if we mash up together some of these equations, let's make another one for our heated guy and our cooled guy. They're both going to cool to the same temperature, we know. And now we can do some cool jazz. If we substitute these two equations, and up here, we can say, bam, oh, get out of my way, little text box, that the look at this big beautiful equation. And so we're going to get this by substituting these two bad boys up into here. I wish that little box would stop appearing. But we can see that, yeah, the mass times the specific heat of the thing that is heated times its temperature change is going to be equal to the mass, opposite though, of the thing that is cooled times the mass specific heat of the thing that is cooled times its temperature change. And we can do this for some fun time math problems. Let's take a look at that, how that's going to go down. So let's say we got a big old chunk of iron. That's at like 15 degrees Celsius. And we place it into 50 grams of sand that is really freaking hot, 400 degrees Celsius. That's some really hot sand. Sand and the iron are left until they reach the same temperature. What is going to be the final temperature of these two dudes together, assuming that no heat is lost to the surroundings? So we have the specific heat of our iron and the specific heat of our sand. Why don't you pause the video, check out that equation from the previous slide, and see if you can do some work on this problem. All right, sick. You tried it out? Well, let's look at how we're going to use it together. So one thing I'm going to do is write out my usual Q equals Q, MC, and delta T, but I'm going to do this for both substances. I'm going to do this for the iron and the sand as well, both of the things that we're studying here. And so I'll go through the problem and record these things. I don't know what Q is, I'm not given that, but I do know the mass of the iron, I know the specific heat of the iron, and while I don't know the exact temperature change, I know the final temperature should be the same for both of these because of that whole thermal equilibrium business. So I can at least write down at this point that TF is equal to, temperature change is going to be the final temperature minus the initial temperature of 15 degrees Celsius. And I can do the same stuff for my sand. I don't know Q, but I do know the mass of the sand. I know the specific heat of the sand, and I don't know the temperature change exactly, but I do know the initial temperature. Well, now I can take what I do know and plug it in to the... So what I can do now is take what I do know and plug it into my friend Q equals MC delta T. You know, even though there's going to be gaps. So with all this down, now I can use Q heated equals negative Q cooled. So which one is heated? This shouldn't matter too much, but let's figure it out. The sand is going to be heated, so I'm going to slap this negative on my iron business. Oh, wait, yeah. But the sand is cooled, rather, so I'm going to slap the negative on that puppy. Gee, get your life together. So I can plug all this business in now, and let's see. Rather, the sand is giving off heat, so it's cooling. Yeah, so it gets the negative. It's losing heat. The iron is absorbing heat, so this negative sign makes sense. All right, so we've got this. Let's simplify for starters. Whoosh. I can multiply these two dudes together. I can multiply these two dudes together. Whoosh. Oh yeah, let's factor this next, because I can multiply this into my parentheses. Oh, and now let's isolate all this TF business to one side of the equation. Very good, very good. Let's get all the non-TF terms to the other side. Very good, very good. All right, now I can divide each side by this 52.75, and that should give me the naked TF final temperature final by itself. Sweet beans. We got a final temperature of 317.9 degrees Celsius. Does that make sense? Well, it's in between these two temperatures, and the specific heat of the sand is greater than the iron, so it's not going to change as much in temperature as the iron. So this makes sense to me. That seems like a good job. Good job. Cool. Let's look at maybe another problem. So why don't you try this one by yourself? Cool. Give it a shot. Follow a similar process to what we did last time. We got you pause the video. Great. You did it? Good. All right, let's talk about it together. We got 50 grams, 500 grams of iron, lead, and it's placed into 1,000 grams or a kilogram of water at 95 degrees Celsius. They reach thermal equilibrium, and we know that the final temperature is 50 degrees Celsius. Oh, so this time we do know the final temperature. What is the initial temperature of the lead? Okay, all right, so let's take a list of what we know. We got lead and we got water. The lead, let's see. We don't know your final temperature, although it's less than that of the water. So we can assume that our lead is going to be heated, and our water, we know the water is getting cooled down. Therefore, the lead's heated. So what do we know about the lead? We don't know Q for this guy yet, but we do know the mass, and we do know the specific heat. We don't know the temperature change, though we do know the final temperature. It's 50, so we know part of this. What do we know for the water? Well, we don't know Q, but we do know the mass of the water. It's a kilo, or 1,000 grams. We do know the specific heat of water, and we do know the temperature change. We know it started at 95 and ended at 50, so 50 minus 95 gives us a temperature change of negative 45 degrees Celsius. Oh snap! We got 3 out of the 4. If you have 3 of the 4, you can go and solve for that fourth dude. Let's do that first. Fine. All right, we'll write down the lead equation first. Pre-planning wine grad, you silly goober. So we have this. Let's solve for Q of the water. Bam! We can just multiply those fools together and get this fantastic number. And if we know Q of the water, we know that the opposite of this number, or the negative inverse of this, is going to be equal to Q for the lead, because Q heated equals negative Q cooled. They're opposites. Therefore, we know Q of the lead is this sweet positive 188,100 joules. 188,100 joules. I just had to say it. So now that we know Q for the lead, we can plug on into this guy. All right, let's simplify that out. Multiply those two together. We'll move our 64 over to the other side, and now we can move our 50 over to the other side, and now we can get the negative. All right, bam! Our initial temperature had to be that can't be right. That's too cold. I mean, the math works out, but that's too cold. Like you can't be that cold, because the coldest it could be is negative 273 degrees Celsius. So clearly I made up a very, very silly problem. But that's what we got. That's the end of this video. I hope you had a wonderful time. Learned a little bit of stuff about how we do science and thermal equilibrium, how to not freeze to death. Don't let yourself come to thermal equilibrium with the winter time. Okay? Don't do that. Ta-ta. Have a great rest of your life.